In this video, we are going to talk about linearly independent sets, which you already know about, as well as bases, which might be new. This is the overview slide that will spend a few minutes just overviewing what we're going to talk about in this video, and then we'll go through each topic in more detail with more examples. We start with this idea of a basis is something that spans a vector space as efficiently as possible. And by efficiently, we mean with linearly independent sets. And to be linearly independent, there's only the trivial solution to this linear combination of all the vectors. So an index set of vectors, v1 through vp, is linearly independent if c1 v1 plus c2 v2 up to cn vn equals 0 has only the trivial solution. The set is linearly dependent if there's a non-trivial solution to the equation. And then we have this theorem: an index set of vectors v1 through vp of two or more vectors with v1 not equal to 0 is linearly dependent if and only if one of the vectors, we'll call it vj, is a linear combination of the preceding vectors, v1 up to vj minus 1. And this definition is for general vectors, where we may be unable to write the vector as columns of a matrix. Remember, vectors don't have to be vectors in Rn. We talked about general vectors in a previous video. So then we get to the definition of a basis. If H is a subspace of a vector space V, a set of vectors B in V is a basis for H if 1, B is linearly independent, and 2, the subspace spanned by B is equal to H. So the two characteristics of a basis is, one, that it spans, just like we said here, the basis spans, and it's linearly independent. That's the idea of it being efficient. We have the spanning set theorem that says if we have a set of vectors in a vector space and we let H equal to the span of those vectors, if one of the vectors in S, say C sub k, is a linear combination of the remaining vectors in S, then the set formed from S by removing V sub k still spans H. And that's because C sub k can be written in terms of the other vectors. 2, if H is not equal to 0, then some subset of S is a basis for H. Once you get rid of all the extra dependent vectors, you'll have a basis. The next thing we talk about is a basis for the nullity of A and the column of A and the row of A. There are a couple of theorems. And then last, we have two views of a basis. The basis is the smallest possible spanning set. And it's smallest because all the vectors are linearly independent. You can't get rid of one of them and still span the same set. Another view is that the basis is the largest possible linearly independent set that spans. So it's the largest possible because if you add another vector, the additional vector will make the set dependent. That wraps up our overview, so now we're ready to look at each topic in more detail. We said that a vector spans a vector space as efficiently as possible, and connected with this idea of efficiency is that those vectors will be independent. So we have this definition here: an index set of vectors is linearly independent if the linear combination of all the vectors equals 0 has only the trivial solution. Whereas they will be dependent if an index set of vectors is dependent if this linear combination that's set equal to 0 has non-trivial solution. So let's look at an example just to review the ideas of linearly independent and dependent. Our first example then is to determine if the vectors are linearly independent, where we have v1 is equal to 1, 2, 3, v2 is equal to 4, 5, 6, and v3 is equal to 2, 1, 0. To see if they're linearly independent, we need to write out this homogeneous equation. So we'll do c1 times v1 plus c2 times v2 plus c3 times v3 equals our 0 vector. So I plugged in v1 here. So I have 1, 2, 3 times, and just because I like the variable x, instead of c1 for my constants, I used x1 as my first constant. Then I plugged in v2 here, 4, 5, 6, and then for my constant, I just substituted x2. And then for v3, I have 2, 1, 0, and I substituted x3. So just to be clear, you could put c1, c2, c3. It's just a constant, so I renamed it x because I like the equation ax equals 0. So looking at this, to see this now is equal to 0, and to see if there's a solution, we put our matrix of our coefficient matrix here, our x variable, and then our 0 vector. To solve this system of equations, these homogeneous equations, then I row reduce the augmented matrix until finally I get that x2 has to equal to minus x3, x1 then is dependent on is equal to 2x3, and x3 is free. I let x3 equal to 1 just because it's an easy number. You could let x3, 0, if you let it equal to 0, that's an even better, easier number, except that then you'd have x1, x2, and x3 equals 0. And we're looking for a non-trivial solution. So really, you could let x3 equals 2 if you want, or negative 1. But I just chose 1 because it's easy. So if I have x3 equals 1, then x2 is going to be equal to negative 1, and x1 is going to be equal to 2. So this means here, substituting back in, that 2 times my vector 1, 2, 3 minus 1 times my vector 4, 5, 6 plus my 2, 1, 0 is equal to 0, 0, 0. So you can see I have a non-trivial solution, which means my vectors are dependent. I'll continue just to note that my 2, 1, 0, I can write that in terms of my other two vectors. It's a linear combination of these two vectors. It's 4, 5, just moving this to the other side of the equation is 4, 5, 6, and then minus 2 times 1, 2, 3. And really I chose this one arbitrarily. I could have solved in terms of 4, 5, 6. If I move that over to the other side of the equation, I could say 4, 5, 6 is dependent on these two equations. It's equal to 2 times 1, 2, 3 plus 2, 1, 0. And I could have solved for this equation, but then I'd have to divide by 1/2. So that, but essentially, one of these vectors can be written in terms of the other two. And this is what it means to be linearly dependent, because there's some sort of redundancy in the system when you have linearly dependent vectors. That means, so for example, here I would say the 2, 1, 0, it doesn't allow us to span any more than the other two vectors, 4, 5, 6, or 1, 2, 3, because 2, 1, 0 can be written in terms of these two vectors. So that's what I mean by redundancy. And also, that's what it means to be inefficiently spanning, is that you have this dependent variable that really, or vector, that can be written, that just repeats information from the other two vectors. In my previous video about vectors, I told you that one thing I like to think of when we talk about abstract vectors or when we generalize the concept of vectors, I like to think of colors. So the colors as a wave is the ideal way to look at this, but I like to think of paints just because I physically like to think of mixing paints. So I can think of vectors as my paint colors. And then my vector addition is mixing paints to make new ones. So if you have an independent set of paints, you cannot duplicate one of your colors by mixing the other colors in your set, such as red, yellow, and blue. You can't get red by mixing yellow and blue, you can't get yellow by mixing red and blue, and you can't get blue by mixing red and yellow. So in that way, these colors are independent. On the other hand, if you have a dependent set of colors, you can make one of the colors by mixing some of the other paints in your set. So, for example, if you had the set red, yellow, and orange, so orange can be made by mixing red and yellow. So being dependent means you can make one of your vectors from the remaining other vectors in your set. To be independent means none of the vectors can somehow be combined to make the same other vector. And now we can define a basis, an index set of vectors, v1, v2 up to vp, of two or more vectors with v1 not equal to 0, is linearly dependent if and only if one of the vj's is a linear combination of the preceding j minus 1 vectors. This definition is for general vectors where we may be unable to write vectors as columns of a matrix. So we saw that when we looked at Rn in our previous example. In this case, we would say j is equal to 3. Our vj vector can be rewritten in terms of the previous vectors. And if we wanted, we could say v2, we could just renumber these vectors. So now if we wanted to number this one as v3 and this is v2, we could say our v3 vector, 4, 5, 6, can be written in terms of the previous vectors. Our next example uses this idea on some general vectors. We're going to talk about the vectors that represent the set of polynomials. So we're going to let p1, our first polynomial, equal to 1. Our second polynomial, p2, is equal to t, and our third polynomial is equal to 4 minus t. And first, we're going to see that p1, p2, p3 are linearly dependent. And why is that? That's because p3 can be written as a linear combination of p1 and p2. In other words, it's equal to 4p1 minus p2, because you'll see if you plug in now, our 4 times p1, that's just 4 times 1, and then minus 1 times p2 is t, so that's equal to 4 minus t, which is exactly p3 of t. So again, it's linearly dependent, and according to this theorem, that means one of our vectors, v sub j, in this case we're talking about p3, can be written as a linear combination of the preceding vectors, that's p1 and p2. We have our next example, which is the set sine of t and cosine of t. We can consider v1, our first vector, sine of t, and v2, cosine of t. And we'll see that they are linearly independent because you can't make sine from cosine by doing linear combinations. So no matter how many linear combinations of sine you get, you're not going to get a cosine, and vice versa. So they're linearly independent on the in the space of continuous functions on the interval 0, 1, because sine and cosine are not multiples of one another as vectors. And that's another way of looking at this is, remember, when you have two vectors, they're linearly dependent only if they are multiples of one another. And you can see that cosine of t is not equal to, I need to put a not equal to, c sine of t. So there's no, oh, I guess actually that doesn't go there, because I'm saying there's no scalar c such that cosine of t equals c sine of t for all t in 0 and 1. Now we can come to the idea of a basis. Let H be a subspace of a vector space V. A set of vectors B in V is a basis for H if 1, B is a linearly independent set. That's the first qualification to be a basis, is linear independence. And 2, the subset spans H. So if B is a basis for H, B needs to span H. Going back to my example of colors, so there are two bases you can have for colors, red, blue, and yellow, and the other bases might be cyan, magenta, and yellow. So you can add other colors here, like if I wanted to add green to this, that would be fine. It would span the same space. However, it would not be a basis because blue and yellow make green, so they would no longer be linearly independent. So the idea of a basis, again, is that they span your space as efficiently as possible. So this is a basis for all colors. And so the nice thing about a basis is, if you think about, let's go out and do some painting at the countryside like Monet or Cassatt, you know, you can bring a nice set of colors, a very nice palette, and you can draw something really nicely. But theoretically, I could just bring red, yellow, and blue and be able to mix any color that you have. Although, personally, I'm not very good at mixing colors, so I wouldn't be able to do that. But theoretically, a person who was good with colors could do that. So, and then I would say I have this particularly elegant set, a very portable set of vectors. It's very efficient. It's the smallest set I can bring and still have the range of colors that I want, which would be all colors in this example. Our next example is, let A be an invertible n by n matrix. Let's say A is equal to A1, A2, AN. These are our column vectors. Then the columns of A form a basis for Rn because they are linearly independent and they span Rn by the invertible matrix theorem. So let's take a closer look at that, and we'll start by looking at the invertible matrix theorem. So we have our matrix A, and then we have the column vectors, and we have It's an n by n matrix, so we have n vectors, and we're looking at Rn. So those are all, it's important that this n here matches this Rn here. So what we have is, if A is an n by n matrix, one, the columns of A span Rn. That meets our first criteria, this criteria here, for a basis. And then second, the columns of A form a linearly independent set. So that meets our second criteria. And that's why we say that the columns of A then form a basis for Rn. And again, it's important that A is n by n, so there are n vectors, and that we are in Rn. If this were Rm, this wouldn't work. This example wouldn't work, because this says Rn for an n by n matrix. Our next example, let E1, E2 up to En, and this is what E1 and E2 up to En look like. It's the vectors with all zeros except in this index, like for 1, except in the first position. If it's E2, then it's 1 in the second position. So zeros everywhere except for this index number. That's where there's a 1. So let that be the columns of an n by n identity matrix In. Then the set of vectors here is called the standard basis for Rn. And we're going to prove that E1, E2 up to En satisfy the conditions of being a basis, but just really quickly, so what we're saying is, let's say for example we're talking about R5, then E1, E2, E3, E4, E5, which look like this, will be a basis for our set, which makes it really easy to find a basis for any Rn. And you can kind of see that they're independent, and we'll prove that in a minute. And second, you can see that they span, because if you have a random vector from R5, A, B, C, D, and I put F because there's already, the E1, E2s, so I didn't want it to be confusing, is equal to A, E1, this is E1, plus B, E2, plus C, E3, D, E4, and F, E5. But let's just go ahead and do this formally. First, we want to show that they are linearly independent, so we're going to write our equation where we have E1 times a constant plus E2 times a constant up to En times a different constant equals 0. So we have this augmented matrix here, but what you can see is that once you saw this matrix, or you can actually just look at it, and you can see that what this is going to necessitate is x1, x2 up to xn. They're all equal to 0, meaning they are linearly independent. And I have this example for n equals 3. So we have our matrix, identity matrix I3, x1, x2, x3 equals 0, 0, 0. When you have your augmented matrix, what you get is x3 is equal to 0, x2 is equal to 0, and x1 is equal to 0. And much like I did just a few slides ago, to show that you span Rn, we're just going to consider a vector x and Rn, and a vector x that's arbitrarily chosen, and so it has coordinates x1, x2 up to xn, and that's simply equal to x1 times E1, x2 times E2, and then x3 times E3 up to xn times e to the n. So this takes care of, we've already shown it's linearly independent, this will take care of the fact that it spans the space. So it is indeed a basis. And it's called the standard basis because it's the easy one, the canonical basis. This next example asks us to determine if V1, V2, V3 is a basis for R3, where V1 is equal to 3, 0, negative 6, V2 is negative 4, 1, 7, and V3 is negative 2, 1, 5. The first thing we'll consider is if this set is linearly independent. So we need to look at this equation, the linear combinations, V1, x1 plus V2, x2 plus V3, x3 equals 0. And I just rewrote it here with 3, 0, negative 6 plugged in for V1 times x1, negative 4, 1, 7 times x2, and then V3 negative 2, 1, 5 times x3 equals 0. So we need to know if there's a non-trivial solution x for this vector equation. And to solve that, we'll look at the corresponding matrix equation, and then we have the augmented matrix with the 0, 0, 0 vector here. We row reduce, and we find that necessarily x1, x2, and x3 are all equal to 0, which means there's only the trivial solution. So far, so good for a basis. It's a good candidate because these vectors are linearly independent. Next, to be a basis, it needs to span the space. And we're looking at spanning the space R3. So to span, that means for any vector B, that AX equals B has a solution. So I have my A here, my augmented matrix B. So B is a representative element, arbitrarily chosen vector. So I'm just going to have the variables B1, B2, and B3 represent my vector B. I do my row reduction. Remember, B, they're numbers, not like these variables. This is our variable. And what we get then is this equation here, which tells us that x1 has to equal to b1 plus 2x3 minus 4x2. x2 is equal to b2 minus x3, and x3 is equal to 1/2 2b1 plus b2 plus b3. So the idea is once you're given a b, let's say our vector b is equal to, maybe it's equal to 1, 2, 3, then you can plug in 1, 2, 3 here and find the x, find the solution. So in other words, because B was arbitrarily chosen or representative of any vector in R3, there is always a solution. So in other words, there's a solution x such that B can be made as a linear combination of our three vectors here, v1, v2, and v3. And therefore, the three vectors span R3. Since v1, v2, v3 are linearly independent and they span, they are a basis for R3. And I have to tell you, I did this first part the hard way. I could have used the invertible matrix theorem, so I'm going to show you that. When I took my matrix A, and I don't even need this last column here, it doesn't have to be the augmented matrix, but I can row reduce my matrix here until I'm in echelon form, and I see that there are 3 pivot positions, or n pivot positions, which means, according to my invertible matrix theorem, 1, the columns of A form a linearly independent set, and 2, the columns of A span Rn. So really I could have just gotten to this point and used my invertible matrix theory, and I could have declared it a basis. I have to admit that I did this problem the first way, the long way, because I guess it just depends on me remembering the idea of basis, and for some reason that sticks in my head. The idea of the pivot position, it just doesn't stick in my head, only because, like, I've taught this class, I'll look at this every now and then. But you know, a year from now, if I haven't seen it, I'm going to be doing it the long way, which is fine, except if you're taking a time-pressured exam, this is the way to go. You can see how much easier it is and faster. So if you have time-pressured exams, I would definitely learn this. And if not, you know, go ahead, do all the calculations like I did. Do it the long way. That's how I normally do it. Our next example, let our set of vectors equal S, which is equal to 1, t squared up to tn. So verify S is a basis for Pn, P of n being the space of polynomials of degree n or less. This basis is called the standard basis for Pn, the canonical basis. First, we have to show that these vectors are linearly independent. So we take each vector and multiply it by a coefficient. So I have 1 times a naught, t times a1, t squared times a2, up to tn times an. And if you remember from algebra how you would solve this, because it's equal to 0, that must mean all of these coefficients equal to 0. To show that they span, let's let P be a random polynomial, an arbitrarily chosen polynomial in the space Pn of degree n or less. So that'll look like a coefficient plus a coefficient times t plus a coefficient times t squared plus a coefficient times to the n. Then a naught, a1, a2 up to an are the coefficients. And so, yeah, essentially, you know, all of our polynomials of degree n could be written in this form, and therefore 1 t squared up to tn span Pn. In the same way that the E1, E2, E3 span Rn, and it's an easy basis, this is the canonical basis for Pn. Next, we have this theorem, the spanning set theorem, that says if S is a set of vectors, P vectors, in a vector space, and we're going to let H be the span of the P vectors. One, if one of the vectors in S, say ck, is a linear combination of the remaining vectors, then the set formed by removing vk still spans H. And two, if H is not equal to 0, then some subset of S is a basis for H. I've moved the statement of that theorem up here so we would have room to do the proof. We are going to start with this first statement here that says if one of the vectors is a linear combination of the others, then we can remove that vector and we'll still have a set that spans H. So we're going to say that VP is our vector that can be written as a linear combination of the previous vectors. And we'll just, renumber the vectors so that VP, we can say previous vectors. But, it really doesn't matter. If we have the vectors, V1, V2, V3, and it happens to be that V2 is equal to some linear combination of V1 plus V3, we can deal with that as well. But the idea is just so that our indices are nice. In this example, we're just going to rename V2 as V3 and V3 as V2 so that we can write this nice little formula here that VP is dependent on the previous vectors. So VP is a linear combination of the previous vectors, so we can write VP as a constant times V1 plus a constant times V2 up to AP minus 1 times VP minus 1. Now, because we want to prove that the smaller set now, the set without VP, still spans, we need to consider a vector x, an arbitrary vector x in our space. So in other words, we're going to consider x and h because we want to say that our set still spans H. So x is in H, and we know that because the p vectors, before we threw out this vector here, so unceremoniously threw it out, we know that these vectors span H, so x can be written as a linear combination of the p vectors. So we'll have C1 V1 plus C2 V2 up to CP VP, since H spans is equal to the span of the p vectors. And you'll notice I put different coefficients here. But now that we have x as a linear combination, we can substitute for this VP, we can substitute this linear combination. So we still have our C1 V1, C2 V2, we still have our CP minus 1, VP minus 1, but now we're going to have CP, and then for VP we're going to put in A1 V1, A2 V2 up to AP minus 1, VP minus 1. Again, this part is just equal to VP that we have over here. So I'm just going to draw this arrow to remind you where we got this VP. Now looking here, because these are just constants times vectors, you can rearrange them, so you can group them. So you can have C1 V1 and then group that with CP A1 V1. So that's going to be V1 times C1 plus CP A1. And then grouping the V2 terms together, we're going to have C2 plus CP times A2 times V2. And we do that all the way up to C of P minus 1 plus CP times AP minus 1 times VP minus 1. So now we have x as a linear combination of our P minus 1 vectors. And since x was arbitrarily chosen from H, right over here, that means that the span of V1 up to VP spans the whole space H. The second part of this is that if H is not equal to the 0 vector, then some subset of S is a basis for H. So if S starts out as linearly independent, then S is a basis for H. If S is linearly dependent, then delete a vector that depends on the others, like we did here. We deleted VP. And we're going to repeat this process until the set is linearly independent and hence a basis. Our next example, we're given vectors V1, V2, V3. V1 is equal to 0, 2, minus 1. V2 is equal to 2, 2, 0. And V3 is equal to 6, 16, minus 5. And we also are told that V3 is equal to 5 V1 plus 3 V2. And we can verify that over here. 5 times V1 plus 3 V2, and it does indeed give us V3. So we want to show that the span of V1, V2, V3 equals the span of just V1 and V2. I'm going to show this here, that the span of v1, v2, v3 equals span of v1 and v2, essentially because I'm showing two sets are equal. I'm going to use the typical strategy of showing the equality of sets as showing that set A is a subset, may not be a property, it's contained or equal to B, and that B is a subset or equal to A, and if both of these are true, then it must be that A equals B. So in terms of our two sets here, first I'm going to show if X is in the span of v1, v2, v3, then X must be in the span of v1 and v2. And then second, I'm going to show if X is in the span of v1, v2, then X must be in the span of v1, v2, v3. These two conditions together will guarantee that the span of v1, v2, v3 is equal to the span of v1, v2. Starting here, X is going to be in the span of v1, v2, v3 over here. And my goal is to show then that X must be in the span of v1, v2. So X is in H, X is in the span of v1, v2, v3. That means that X is a linear combination of v1, v2, v3. And then I am also given that v3, where is this? Over here, that v3 is equal to 5v1 plus 3v2. So now I can write X as cv1, cv2, and then plugging in here for v3, c3, 5v1 plus 3v2. And just doing algebraic manipulations, I'm going to group my v1s together, and I get c1 plus c3, 5c3 times v1, plus c2 plus c3 times 3 times v2. So now what I have, so X now can be written as a linear combination of v1, v2. So X is in the span of v1, v2, since, right, this c1 plus 5c3 and the c2 plus 3c3 are scalars. So if X, what I have shown then is if X is in the span of v1, v2, v3, then X is in the span of v1, v2. Now working on this second statement, I want to show that if X is in the span of v1, v2, then X is in the span of v1, v2, v3. So we'll start with X is in the span of v1, v2, then X can be written as a linear combination of v1 and v2. And then I can write X as a linear combination of v1, v2 plus 0, v3. So now X is a linear combination of v1, v2, v3, and then for X is in the span of v1, v2, v3. So I've shown both of these statements here, and I can conclude that the span of v1, v2, v3 is equal to the span of v1, v2, this over here. So I shrank all that work here so that I can work on the next problem, which is to find a basis for v1, v2, v3, or the span of v1, v2, v3. And remember, we already know v3 is dependent on v1 and v2, so we're not even going to consider that as our basis, as part of our basis. All we're going to look at is v1 and v2. We also know that v1 and v2 span H, the span of v1, v2, v3. So the only thing we need to know is if v1 and v2 are linearly independent, but we can see they are not scalar multiples of each other. And remember, when we have only two vectors, they're only linearly dependent if they're scalar multiples. So since they are not scalar multiples of each other, they are independent, and therefore they're independent and they span, and therefore v1, v2 is our basis for H. Now we're going to continue onward, and we're going to look at basis for the null of A, which, you know, actually a lot of people put NUL of A, but right, it only saves one character. So I usually just write out null of A, the column space of A, and the row space of A. And our example would be to find a basis for the column space of B, where B is equal to 5 column vectors that are equal to 1, 0, 0, 0, 4, 0, 0, 0, 0, 1, 0, 0, 2, negative 1, 0, 0, and 0, 0, 1, 0. So that's nice. This is already reduced for us. So what we want is a basis for the column space of B. So I'm going to write that out. The column space is the span of our 1, 2, 3, 4, 5 vectors. So we need to find a linearly independent subset. We know it spans the column space of B. We need a linearly independent subset. And I will tell you there's an easy way to do this that we will see in our next theorem, but I'm going to do this the hard way since I haven't mentioned that theorem yet, and also I guess it'll give you practice on seeing linearly independent subsets. So to find if they're linearly independent, you set, the matrix AX equals 0. So here's the augmented matrix. And you'll find that x5 is equal, well, because it's already row reduced, that's nice. So x5 is 0, x4 is free, x3 is equal to x4, and x2 is free, and x1 is equal to minus 4x2 minus 2x4. So I'm going to let x1 and x2 equal to 1 because it's a simple solution, which will give me x1 is equal to negative 6, x3 is equal to 1, and x5 is equal to 0. So this is what it looks like. My negative 6 times my first vector, 1, 0, 0, 0. My 1, because x2 is equal to 1, times my second vector, 4, 0, 0, 0. x3 is also equal to 1 times my third vector, 0, 1, 0, 0. My x4 is also equal to 1 times 2, negative 1, 0, 0. And then x5 is equal to 0 times 0, 0, 1, 0. And that will give me 0. And what I see is I chose B4, the fourth vector here in my matrix. I chose to say that that is dependent on my other 1, 2, 3, 4 vectors. It's equal to 6b1 minus b2 minus b3, and technically I should have said plus 0 b5. So the next thing I did is I looked at my remaining 1, 2, 3, 4 vectors, so I can see if there's anything that's linearly dependent. And I can see that just looking at this matrix, I can see that b2 is equal to 4b1. So I can eliminate now the second vector. Once I eliminate this vector here, the b2 vector, I am left with 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. In other words, I'm left with e1, e2, and e3. We know they're linearly independent, and you can certainly verify that if you'd like, but they're linearly independent, and they span the space, and therefore they are a basis. And as I mentioned, there's an easy way to do this. We have a theorem, which we'll see next, that says each non-pivot column of B is a linear combination of the pivot columns. So looking at our matrix, where are our non-pivot columns? This is our non-pivot column. Well, our pivots are here. They're whenever you have a leading 1. So these are our non-pivot columns, or those are exactly the two that I chose to eliminate. I mean, you could have eliminated over here at this point. You could have chosen some other linear combination and gotten another set. The bases are not unique. There's more than one basis for a space, but this is the easy way of getting a basis, is looking for the pivot column. So again, this is another example of where if you know what a pivot column is and you know the theorems regarding pivot columns, this is really easy. But you could do it this hard way if you are not time pressured. And again, this is our new theorem. The pivot columns of a matrix A form a basis for the column space of A. We have another example. It can be shown that A equals A1, A2 up to AN columns is row equivalent to B of the last example, and we want to find a basis for the column space of A. Here I am given this matrix A, which is equal to, it's going to have what, 5 vectors, 1, 2, 3, 4, 5. My first column vector is 1, 3, 2, 5. My second column vector is 4, 12, 8, 20. My third column vector is 0, 1, 1, 2. My fourth column vector is 2, 5, 3, 8. And my fifth column vector is negative 1, 5, 2, 8. And we're saying that this is row equivalent to B from our last example. And from our last example, we took these pivot column vectors to be our basis. And we noted that B2 was equal to 4B1, and we solved to find that B4 is equal to 2B1 minus B3. So this is our background information, and now we want to find a basis for the column space of A. And of course, we could just find a basis for the column space of A, but the idea is to relate these two. And since row is equivalent to B, then what that means is the matrix equation AX equals 0 and BX equals 0 have the same solution. And what that exactly means that if X, from when we were solving for B, is equal to minus 6, 1, 1, 1, 0 is a solution to BX equals 0, i.e. that is if you take minus 6 times the first column vector 1, 0, 0, 0, plus here 1 times the second column vector 4, 0, 0, 0, plus 1 times the third column vector 0, 1, 0, 0, plus 1 times, is that right? Yeah, 1 times the fourth column vector 2, negative 1, 0, 0, plus 0 times the fifth column vector 0, 0, 1, 0, you're going to get 0. But since A is row equivalent to B, that means the same vector x, my minus 6, 1, 1, 1, 0, is a solution to AX equals 0. That is, I'll take negative 6 to my first column vector, 1, 3, 2, 5, plus 1 times 4, 12, 8, 20, plus 1 times 0, 1, 1, 2, plus 1 times 2, 3, 5, 8, plus 0 times my last column vector is, actually I wrote the wrong column vector, let me change that. 0 times the last column vector, negative 1, 5, 2, 8, equals 0, 0, 0, 0. This is an 8 here. And I wrote this out in painful detail, but I wanted to tell you that the column vectors of B are related in the same way as the column vectors of A. That is, if B2 is equal to 4B1, which we had from when we were working our last example, and we also know that B4 is equal to 2B1 minus B3. That means that A2, the corresponding vector A2, will be equal to 4A1, and you can verify that right here. And also A4 will be equal to 2A1 minus A3, and you can verify that as well. Which means that A1, A3, A5 will be a basis for the column space of A. And you want to be really careful not to make the mistake of using the column vectors of B, saying, oh, these are row equivalent. That must mean this is also a basis for, the basis here of B must be a basis for A. That is not true at all, because this is not a basis for A. You have to find the equivalent, the corresponding vectors in A to be a basis. Now we have a second theorem for this space. It looks sort of like we're going to start with the same thing as our last example, but it's a different result because it's on the row space. So if two matrices A and B are row equivalent, then their row spaces are the same. If B is an echelon form, the non-zero rows of B form a basis for the row space of A as well as that of for B. So this is totally different from the column space which we just saw, the example we just saw. Our example for this theorem here is find a basis for the row space of matrix A from the last example. So here's our matrix A. It was row equivalent to matrix B. So the basis for row B, the row space of B, is equal to the row, the rows written as vectors. So the row vectors. So 1, 4, 0, 2, 0, 0, 0, 1, negative 1, 0, and the 0, 0, 0, 0, 1. We don't need the last 0 because this is all 0 on the last row. We don't need that. So that means now the row space for A is the same as the row space for B. So this is totally different, and that these two you can say are equal. You cannot do that for the column space, as our last example showed. The last topic we have is our two views of a basis. That is, the basis is the smallest possible spanning set. And it's the smallest because all vectors are linearly independent. You can't just throw one out. If you throw one out, you're going to lose some information because each vector has its own piece of information it's contributing. Second, the basis is the largest possible linearly independent set that spans, because if you add something, all of a sudden you're going to have a dependent set because the set already spans. So here we have the two views of a basis, and this is our example to illustrate that. We have three sets in R3, and they show how a linearly independent set can be enlarged to a basis, and how further enlargement destroys linear independence of the set. Also, a spanning set can be shrunk to a basis, but further shrinking destroys the spanning property. So let's look at this. Here we have two vectors in R3, they're three-dimensional, but they do not span R3. In particular, you can't get anything with the last coordinate here, right? You can only get, all linear combinations will only have something on the first coordinate, something on the second coordinate, and they'll always have 0 on the last coordinate. So this does not span R3. But you can add a vector, in this case 4, 5, 6, that will allow you then to get things on the third coordinate. And I haven't shown that these three vectors, all three together, are linearly independent, and I haven't shown that they span R3. But I'm going to leave that to you, but tell you that they both are linearly independent and they span, so they're a basis for R3. So again, this is the idea. If you have a linearly independent set, you can enlarge it to a basis. And of course, when you enlarge it, you can't just throw in any random vector. Like if I had thrown in 0, 1, 0, that wouldn't have helped. So you have to throw in one that's both linearly independent, make that the set's still linearly independent, and you have to throw in one that will help you span the space. The second thing, though, is once you have a basis, further enlargement will destroy linear independence, and that's over here. So now we have our basis, and we just threw in this extra vector. And the reason why it destroys linear independence is we already know that these three vectors span the space because they're a basis. So that means this vector here, the one we just threw in, can be written as a linear combination of these three vectors. And if it can be written as a linear combination, it's dependent. So once you have a basis, adding more vectors will destroy the linear independence, and you'll no longer have a basis. You'll still have a spanning set, but you won't have a basis, which is the efficient spanning set. And you can also think of this theorem going the other way. So we can start with the spanning set, and by that theorem, the spanning set theorem, we can throw out things that are linearly independent, or linearly dependent, sorry, until we finally get to something that is a basis. And then again, the basis is the smallest possible spanning set. So if we throw something out from here, any one of these vectors, we're no longer going to be able to span the set. So that's this idea here. Now that we have covered all the ideas in this video, I have 3 more problems, but since we've covered everything, I'm going to suggest after each problem statement you pause the video and give the problems a try or some thought before you look at the solutions. The first problem is determine if these two vectors v1 and v2 is a basis for R3, and then the second question is v1 and v2 a basis for R2. Our vectors v1 is equal to 1, negative 2, 3, and v2 is equal to negative 2, 7, negative 9. The first thing I'm going to say, since there are only two vectors, it's easy to check they are linearly independent because they're not scalar multiples of each other, right? To get the first coordinate to 1 to get to negative 2, you'd have to multiply the vector by negative 2, but then that would mean the second coordinate multiplied by negative 2 would be 4, not 7. So they're not scalar multiples, so these vectors are linearly independent. The second thing you need to check for is if they span R3. That's the rest of this writing. Do v1 and v2 span R3? So we need to consider an arbitrarily chosen vector b in R3. So we're just going to label it b1, b2, b3 so that it can represent any vector in R3. And the idea is, does this matrix equation with the first column vector equal to v1, 1, negative 2, 3, and the second column vector equal to v2, negative 2, 7, negative 9, times x equal b1, b2, b3 always have solution? I row reduced it, and what I get is that b1 has to equal to b2 times b3. So that means, b1 has to equal to b2 plus b3. And just writing that out again, our b is equal to a linear combination of our v1 and v2 only if b1 is equal to b2 plus b3. In other words, only for vectors in R3 that look like b2 plus b3, b2 and b3. So v1, v2 does not span R3 and therefore is not a basis. As we noted, v1 and v2 are linearly independent, but it fails to span. We have one more question. Is v1, v2 then a basis for R2? And the answer, it is no, because it's the wrong dimension. R2 looks like, right? They look like this. Some vector x with 2 coordinates. But here we have v1 and v2 having 3 coordinates. They're like in a totally different universe. Wrong dimension. The next question, find a basis for the subspace W spanned by v1, v2, v3, v4, where v1 is equal to the vector 1, negative 3, 4, v2 is the vector 6, 2, negative 1, v3 is the vector 2, negative 2, 3, and v4 is the vector negative 4, negative 8, 9. Well, we know that the vectors span, so all we need to do is get rid of all we need to do, as if it's easy. But what we need to do then is get rid of any linearly dependent vectors. So here I have, but you know what? I was going to set it up equal to 0, but there's that theorem we have about the pivot columns. So I have this and I row reduce my matrix. I identify my pivot columns because I'm good about this now and remembering that theorem. These are my two pivot columns. So that means my first and second vectors, 1, negative 3, 4, and 6, 2, negative 1, is a basis for the space spanned by v1, v2, v3, v4. And just for your reference, I wrote down the theorem I was using. The pivot columns of a matrix A form a basis for the column space of A. And so this is exactly what we're looking here, right? The space spanned by v1, v2, v3, v4 are all the linear combinations of v1, v2, v3, v4, because that's the definition of span. But that's also the definition of the column space of A. So that's, I always forget this pivot column theorem, but here it is. It makes life much easier. If you didn't remember this theorem, you would have to set this equal to the AX equals 0. So you'd row reduce 0, you'd find one of the you'd have to do that twice because you'd eliminate one vector and then you'd have 3 remaining vectors. You'd row reduce again, find the other vector that's dependent and eliminate it. This last problem, let v1 equal to the vector 1, 0, 0, and v2 equal to the vector 0, 1, 0, and h be the set of vectors that have the form SS0, where S is a real number, so I rewrote this in column form. Then every vector in H is a linear combination of V1 and V2, because H equals SS0 is equal to S times V1 plus S times V2. The question is V1, V2 a basis for H? So this problem is tricky because you're really led down the garden path. First, you're shown that V1, V2 spans H, right? It's demonstrated that H is equal to SS0, which is equal to S times 1, 0, 0 plus S times 0, 1, 0. And 2, you can look at these two vectors, 1, 0, 0 and 0, 1, 0, and you can see they're linearly independent. They're E1 and E2. But the thing is V1 and V2 is not a basis, and basically this is a trick. And the trick comes because when we break SS0 into component vectors, usually we factor out the same constant, so we get S times 1, 1, 0. In other words, 1, 1, 0 is our basis. And just again, to look at this again, the SS0, so for example, and this is a different problem in blue, but I'm just kind of trying to clarify this point. If our space looked like vectors 3a plus 2b, a, and then 4b, we would have broken this up into a times 3 times 1 times 0. So we would have had the 3, 1, 0 vector times a plus the 2, 0, 4 vector times b. So in this case, because S, this is the same constant twice, we really should have broken this SS0 into S times 1, 1, 0. So this is the basis. Furthermore, your textbook says that 1, 1, 0, that's the basis of a line, right? Because it's a single vector, so you can scale it. So you basically get other points on the line. But V1, V2 spans a plane, so it can't be a basis. It's too much information, right? It's too big. So it's a single vector that will span the space. Oh, there's one more problem. I lied. It wasn't the last problem. It wasn't just 3. There's 4. So let V and W be vector spaces. Let T be a transformation from V to W, and U be a transformation from V to W, and they're linear transformations. And we're going to let V1 up to VP be a basis for V. If T of Vj equals U of Vj for every value of j, so every corresponding vector v1, t of v1 is equal to u of v1, t of v2 is equal to u of v2, all the way up to t of vp is equal to u of vp, show that t of x is equal to u of x for every vector x in V. So we wrote what we were given. T of Vj is equal to U of Vj for all j between 1 and p. We're going to consider x and v because we want to show that T of x is equal to U of x. So if x is in V, then we know that x is a linear combination of our bases because v1, v2 up to vp is a basis for v. So x is written as a linear combination, again, since these vectors are a basis, and these basis vector spans v. So now when we plug in x into t, so t of x is equal to, and then I wrote my linear combination out, x1 v1 plus x2 v2 up to xp vp. Now since t is linear, we can pull out the scalars and also separate out each term. So we have x1 t of v1 plus x2 t of v2 plus xp t of vp, again because t is linear. But now we're given that t of v1 is equal to u of v1 and t of v2 is equal to u of v2, again because this is what we were given, t of vj is equal to u of vj for all j between 1 and p. And so finally we have x of p is equal, t of vp is equal to u of vp. And again, that's from our given. And now this, we can use our definition of linear backwards, and we can say that this is equal to u of x1 v1 plus x2 v2 plus up to xp vp, since u is linear. And finally, this is just equal to u of x. So we have shown that t of x is equal to u of x. To review what we covered in this video, first we talked about bases being bases are something that span a vector space as efficiently as possible. We reviewed the idea of being linearly independent, which means a linear combination of all our vectors equals 0 has only the trivial solution, whereas if it's linearly dependent, a linear combination of all our vector set equal to 0 has a non-trivial solution. And then we have this theorem here. If we have a set of vectors, of two or more vectors with v1 not equal to 0, if it's linearly dependent, or it's linearly dependent if and only if there's some vector, v sub j, that's a linear combination of the preceding vectors. In other words, to be dependent means you can write one of the vectors as a linear combination of the remaining vectors. And this definition was good for general vectors where we may be unable to write vectors as columns of a matrix A. That led us to the definition of basis. So let H be a subspace of a vector space H, then the set of vectors B and V is a basis for H if 1, B is linearly independent, and 2, the subspace spanned by B is equal to H. So the two things about a basis is they will span your space, and 2, it's efficient, and by efficient we mean linearly independent. There's no repeated or extra information that you can just throw out. So we have this theorem about a spanning set theorem as well, which said if we have p vectors and we let H be the space spanned by the p vectors, then if one of the vectors in S, let's say ck, is a linear combination of the remaining vectors, then the set formed from S by just throwing out v sub k still spans H. And 2, if H is not equal to 0, then subset S is a basis for H. We also looked at the basis for the null space of A, the column space of A, and the row space of A. We have this nice theorem here, if you can manage to remember what a pivot is. Now I sort of do. But the pivot columns of a matrix A form a basis for the column space of A, and make sure you're looking at the pivot columns of A. 2, if two matrices A and B are row equivalent, then their row spaces are the same. So if B is in echelon form, then the non-zero rows of B form a basis for the row space of A, which is quite different from this column space. We have this two views of a basis. The basis is the smallest possible spanning set. And it's the smallest possible because the vectors are all linearly independent. So you can't just throw one out because each one contains kind of unique information that you need to span the set. Also, the basis is the largest possible linearly independent set that spans, because an additional vector, since the basis already spans, an additional vector will be dependent. So you have these two views over here. So that's it for this video. Thank you for watching.